So this comments then as to why we could imagine that you could make this happen on Earth is the requirement here is actually not so much around the energy, because for almost 100 years, we've actually induced fusion reactions on Earth with particle accelerators. This is one of the first things that was discovered, actually, when particle accelerators were developed in the 1930s. The question is about how you maintain the temperature of this medium, of the hydrogen fuel, that allows it to stay hot enough for it to keep fusing. And the sun and stars work by the fact that how is it allowed that the center of the sun is so much hotter, 20 million degrees? Then how can it not this heat escape? Well, it does escape with finite probability or timescales, but are very long timescales, like orders of 1 million years or something like this. And the reason this is happening is because it's the sun's own gravity, which is containing this hot core, which disallows it to escape and dissipate and therefore cool down and then stop the fusion reactions from occurring. So this is why as it turns out, gravity is the weakest of the fundamental forces by a lot, like many, many orders of magnitude. And so for this reason, in order for fusion to be viable on Earth, you can't do it by the exact same process that a star works, because it takes something the size of a star. So with a few exotic sort of examples like neutron stars, this is why stars are actually enormously large, because gravity is a very weak force. So this ironically, in some sense, it comes back to what I just commented to. The thing that makes fusion hard is this electrostatic repulsion that is occurring because the two like-charged particles, they both have positive charge, don't want to get close together to fuse. We actually use its cousin, which is the magnetic force, is one of the ways to do this. We replace that gravitational force, which is something which has much higher effectiveness than gravity. And primarily what we use is the electromagnetic force. And so that's what we, in fact, primarily use on Earth. Although it's not exclusively that, it's mostly that's the thing that we use to sort of recreate these temperatures, particularly that occur in the interior of the sun. So I think your last question was why isn't that crazy? Like, it seems dangerous for something to have something at such high temperatures on Earth. It's actually the opposite of that. And it comes from a little bit of a subtlety of understanding the thermal balance in a fusion system, is that while the materials, this fuel gets extraordinarily hot, there's extremely little of the fuel, like very, very little of the fuel. So one of the leading concepts, for example, that's the focus of my own research in magnetic confinement, the energy content of the fuel, even though it's at 100 million degrees, is less than boiling water. Because there's so few particles in it. So you actually you basically need, in order to have something that has high energy content and therefore could be considered dangerous, it has to have high temperature and large numbers of particles of it. So fusion has very high temperature, but very, very few particles. So when you put those numbers together, it turns out it's not dangerous at all. And the other thing that makes it safe is because what makes fusion hard on Earth is, in fact, isolating it from anything that is terrestrial, anything that's Earth-like, anything that has root temperatures, anything close to what we're used to, is that what tends to happen is this fuel will just leak its heat so fast into that medium, it cools down and immediately stops making fusion. So, in fact, fusion has inherent safety built into the physics of it. It's actually not really a engineering safety concern. You can't actually, in many ways, you can't actually use it intentionally to do bad things with it because of those physical properties of the fuel.
Okay, so let me see if I've got this straight so far. So a star aggregates together primarily hydrogen because of gravity. And if there's enough aggregated together, the gravitational density, especially in lower levels of the star, becomes such that fusion reactions can begin to take place. Now, is that primarily because initially is it that the atoms are crushed together despite their electromagnetic opposition? They're crushed together by the pressure that's a secondary consequence of the gravity. So they're just brought into proximity. And and what happens? Does like one fusion reaction take place and then start a chain reaction under the appropriate conditions?
Yeah. So no, actually, which is the other part of. Thanks for asking that. That's a very insightful question. Actually, it doesn't work through a chain reaction. It works rather through a thermal process, which is different. Let me just quickly explain this, because this is a fundamental difference to fission. So in fission, what happens? You imagine. So here's your great big uranium nucleus, right? And the fission gets triggered by an extremely simple process in many ways. It's a neutron, which is one of the components of the nucleus, which is made of neutrons and protons. Neutrons have no electric charge, protons have electric charge. They hold themselves together in the nucleus through the strong nuclear force. A neutron, which can participate in that force, basically gets in proximity to the uranium nucleus, and it splits apart and releases energy. It also releases neutrons when it does that. And so when those neutrons leave that as a cause of that reaction, if you design the assembly of the uranium in that case, or other materials which can undergo fission, what you do is you design it such that it's that particle that actually starts the next reaction. So in a power plant, like in a fission, nuclear power plant, you design this very carefully and control it very carefully, that on average, when one fission reaction occurs, one particle that is released from that triggers the next fission reaction, and you control that. If you intentionally don't control that, then the process runs away, because that one, say, triggers 2 more fission reactions, and then 4, 8, 16, and up it goes, and in fact, that creates an explosion. Fusion does not work that way because the products that are made by fusion are very, very hard to fuse. They actually don't trigger the next fusion reaction. So in fact, that almost comes by definition, because what's happening is primarily it's converting the fuel into helium, and helium is an extremely stable nucleus. It actually doesn't want to fuse anymore. That's actually why fusion is such a good process and such an energy efficient process. So it's not that particle that wants to fuse anymore. It's the heat which is released from the fusion reaction that gets the fuel a little bit hotter. If you get it a little bit hotter, then that will want to make more fusion reactions. And as it releases heat, it'll actually get the fuel hotter and it will go up.
Why is it more likely we talked about the relationship between gravitational pressure and the preconditions for fusion. Why is that more likely at higher levels of temperature?
Right. So that does come from the fundamentals of the process. So if you take a single reaction of fusion and you consider the average energy of the particles, that in general, although there's a limit to it, as you increase the average energy, the velocity, essentially, the particles to fuse, that gives them a higher likelihood of overcoming the repulsion.
Because they're in motion.
And then basically allows them to do that. And that's a good one to speak about, because as I commented before, accelerators, in fact, I have an accelerator run by graduate students at MIT that can trigger fusion reactions all day long, because you take an accelerator, you give a single particles back basically a high average energy, and you impinge them onto a target that's of appropriate composition, you'll trigger these kinds of fusion reactions all day long. That cannot make net energy. It turns out it's because what's happening is that basically most of the energy that you're supplying to this particle just gets lost in useless heat, essentially, in the system. What's happening inside of stars, and that's why I said temperature, not energy, is that it's a contained thermal system. What I mean by thermal, this means it's the equivalent, that we're used to of thinking about, like we think of water of having a temperature or air of having a temperature. This medium, which is called a plasma, actually has a temperature. It is a system in which the particles have a distributions of energies based on thermodynamics. And so that's why I call it a temperature. So this is key. It's a thermodynamic process in that sense, is that you have something inside of it, is that individual particle reaction releases kinetic energy, but because that's forced to give that energy back as heat into the medium, the temperature increases, the average energy of the particles in the medium increases the probability, and this
Right.
builds up your way to actually to being able to
I
do
see.
that.
So you crush them together, and that increases the probability of fusion to some degree, and then you heat them up, and that increases the probability even further.